Okay, so today we have a very special guest, Antoine Bourget, who will tell us about generalized toric polygons, T-branes, and 5D SCFTs. Take it away.
Thank you, Julius, and thanks everyone for coming to this talk. Always nice to speak at the Quiver Meeting. There will not be that many quivers today, I fear, but a few, and I hope you will still like it. So this will be based quite closely, actually, on the recent paper from last month, written with Andres Colinucci and Sakura Shefanemeki, who I don't know if they are in the audience. I don't think so. So I will have the responsibility for telling you what we did. And so let me first, so it will be like, as you see, it's a Blackboard talk. I would give a Blackboard talk if there was a Blackboard. So this is the closest approximation I got. So don't hesitate, of course, to interrupt me and ask questions as we proceed. So what's the question that we are asking? So the context is 5D SCFTs. And as we all know here, I think, 5D SCFTs, from the point of view of field theories, they are quite difficult objects to handle. And the reason why we know they exist is basically because of string theory. So string theory is telling us that those objects should exist, and it allows us to characterize them in some sense. And there are two main, well, at least two main approaches to see that 5D SCFTs should exist in string theory. Actually, there are more, but the original reasoning by Seiberg is a bit different from what I will be talking about here. What I refer to here are the constructions in string theory, which are broadly in two classes. One is as M theory compactified on well, R1, 4, so this is your 5D spacetime, times, say, X, and X is a local Calabi-Yau threefold. If you put M theory there, then you get at the tip, so let's say local Calabi-Yau threefold, which is some singular. And at the singularity, you might have some 5D SCFTs, provided this Calabi-Yau satisfies certain conditions. And another big class of constructions for 5D SCFTs are the type 2B brane webs. So 5 brane webs, I should say. So which are brane webs of PQ 5 branes. So you have D5 branes, NS5 branes, and on the world volume of the intersection of all those branes, you also have some theory. And also under some conditions, it should be a 5D SCFT. So the point here is to see how those two constructions are connected. And so in this introduction, let me spend some time telling you about those things. So I won't give many citations because I have to write and it takes time. But of course, there is also a massive body of work on all those approaches. So I won't really mention them. All the references, of course, are in the paper. So the first approach here, the M theory approach, I will refer to as the geometric approach, because the data about the SCFT is stored in this Calabi-Yau X, while this one I will refer to as the brane approach, or the brane web approach, because we are now on flat space-time, but the data about the theory is stored in the brane web and how the branes intersect and so on. So both approaches have been extremely successful at exploring SCFTs and giving various data about them, like global symmetries, description of the moduli space of vacuum, and also trying to classify the theories, etc. So for instance, here for the geometric approach, I can mention the work by Jefferson, Katz, Kim, Waffa, and others, where they try to formulate geometric conditions on X so that really this engineers a 5D SCFT. And using these conditions, you can attempt at classifying, at least for low rank, classifying the various theories. And in particular, at rank 1 and rank 2, they provide a relatively complete classification. So that's very nice, and it gives list of SCFTs, in particular at rank 1 and 2. And in principle, you can try to go on. You have building blocks of the geometry, and they should satisfy certain conditions, and you should assemble them in a certain way, and that way you can explore. With brane webs, you can also basically do whatever you like. You take intersection of branes, so vertical will be my NS5 branes and horizontal D5 branes, and you intersect. And again, provided you can shrink this to 0 size, this is the brane analog of some condition on the shrinking of 4 cycles and 2 cycles in the Calabi-Yau, you can realize various SCFTs. And now the natural question is, what is the connection between these two approaches? Is there a connection? And there is one case where it's very beautiful, it's well known, that if you take a brane web, you can take the dual diagram to this. So for the one I've drawn here, that would be something like this. So you put, I'm looking only at the outside, because only the outside of the brane web is relevant for defining the SCFT. The SCFT will be reached when everything here in the middle is shrinked to 0 size. So only the outside matter, and the outside defines a polygon like this with vertices which are on Z2. So it's a Z2, sorry, it's a Z2 polygon. And now this polygon you can interpret as a toric polygon, which defines a toric fan. So if you are in 3D, now you can put this polygon here on the plane. Should have drawn in another color. You're in 3D, and now this polygon you put in the z=1 plane, like this, and now this generates a 3-dimensional fan, and then this generates some toric variety, and this toric variety is precisely X. So in the case where X is toric, you can also go the other way. If X is toric, then it has a toric polygon associated to it, and you can draw this polygon, draw the dual diagram, and then it gives you a brane web. So in other words, we can draw the following thing. If you start from a polygon, I'll draw this here, a polygon which should be convex in Z2, you can either interpret it as a toric diagram for some from some toric Calabi-Yau threefold. So this is using toric geometry. This is toric geometry. Or you can dualize it. So you take the dual, and then you get a brane web. And then once you have these two things, you can use M theory on this toric Calabi-Yau, and you obtain some 5D SCFT. Or you can take the brane web and look at the world volume, and you get the same. So this will be just looking at the world volume, and you get the same 5D SCFT. So there is this very nice kind of dual approach, and this is just given by duality. Okay, well, I wrote it here already. So now the question is, if we go back to the story here, and if you look, for instance, at the classification of 5D SCFTs that is obtained from the geometry at rank 1 and 2, you notice that there seem to be many more SCFTs than what you can get using just toric geometry. And the same was observed with brane webs. Already at rank 1, actually, if you try to have a rank 1 brane web, it means in terms of the dual diagram that you have only one internal point, or here only one face. Then you're very limited in what you can do, and it appears you cannot do, for instance, the exceptional theories. So well, I should maybe have given an example here, which dates back to Seiberg. If you take SU2 gauge theory with NF fundamentals, then Seiberg showed that this realizes the ENF+1 SCFT. And if NF is such that this E is really exceptional, so it gives E6, E7, or E8, then you cannot realize it just with a brane web like this. There will be too many flavors, and the dual diagram will be non-convex. But a long time, well, 15 years ago, Benini, Benvenuti, and Tachikawa showed how you can actually accommodate for this if you enlarge the class of polygons that you have and you allow for white dots, which will account for the non-convexities. So maybe I should give an example of this, and then I will complete this diagram here. So if you have, for instance, a brane web where you try to do SU2 with, let's say, with 5 fundamentals, then the brane web looks like this. You take something like this, something like this. So this is SU2 because you have 2 D5 branes over here, and then there are 4 flavors: 1, 2, 3, and 4. These external branes, or you can end them on D7 branes. But then if you want to add the 5th one, then you can add it here, for instance, as a 7 brane as well. But then if you do this and you try to go to 0 size to get the SCFT, well, you cannot do it because the 7 brane is stuck here in the middle. So, okay, you can take it out using a Hanany-Witten move. So you take it across here, and then it becomes this. And now if you draw the dual diagram, you get something like this. And this is a non-convex polygon. Now, how to deal with this? Well, the idea is that those can be taken across. So here there are 7 branes, so they have monodromy cuts in this plane. Each of them has them, but these 2 are important. And you can therefore use this monodromy cut to take this brane and do this. And this angle here is due to the monodromy cut. So there is still charge conservation, even though it appears that there is not. And now once this is done, you can take this one and move it across here. And because of the Hanany-Witten effect, you have a brane creation over here. And so this non-convex polygon is actually cured by adding this little element here, which is this part here. And as you can see, now you have a non-trivial boundary condition on the 7 brane here. Here there are 2 5 branes ending on 1 7 brane. This is a specific boundary condition, and this is accounted for by this white dot, which here appears black because I'm on a blackboard. That's okay. So this is white. This is black for me. Okay, and so clearly you have to accommodate for those guys. So these things here are sometimes known as generalized toric polygons, or GTPs, because they are like toric, but they are generalized with these white dots. And the question is, how do you interpret these white dots? So before going there, just let me mention one more thing, which is that here, as you see the white dot, I obtained it from some non-convex polygon, the one which is drawn here in white, and then I've made it convex by doing this game with the monodromies. This in general is not easy to do, and sometimes it's not possible to do it. Like if you try to put too many flavors, like if you replace this 5 by 8 or more, then there will not be any way to make the polygon convex. So actually a slightly simpler idea is to really take this seriously and to start from here. So we are just taking polygons, which are always convex. So I will impose that they are convex, but I will allow to have white dots. And therefore I'm sure that the thing is well defined. And then I can always go from here to a brane web by just taking the external edges as asymptotic branes, and then the white dots tell me what are the boundary conditions. So the question now seems to be, you take a generalized toric polygon over here, and you ask, what is the 5D theory? Well, as we say, you can easily dualize. This works as before, and it gives you a brane web. The only difference is that it has now a boundary condition, like this one here, but it's perfectly well defined. And then the world volume is also perfectly well defined, and you get a 5D SCFT. Now, now the question is, of course, these things are not toric polygons, so there is no notion of toric geometry. So this arrow here is missing. But we also know from the classification that I mentioned above here, like those things are known. We know some Calabi-Yau which generate those things. So M theory is also able to realize those same SCFTs. So this is still M theory. So all of this work. The one thing which is missing is this arrow. So, and here it cannot be toric geometry. So it's some other thing, some non-toric deformations. So it's non-toric Calabi-Yau 3. And the question, the goal of this talk is to try to say something about this, this arrow here, really based on the polygon. Again, the Calabi-Yau here is known in some cases from the pure geometry. But here the goal is really to take the GTP and to try to characterize it, and to characterize it as a deformation of the toric Calabi-Yau you would have without having the white dots over here. So that's the goal of the talk. So are there questions at this point? Okay, so now, okay, how do we approach this? So I've explained the first word and the last one, but I have not talked about T-branes. So where are the T-branes going to enter? Well, the T-branes enter in the approach we are taking to solve this problem. So I lost the here. Okay. So the idea that we use to solve this problem is to consider a toric polygon. So let's take, for instance, a triangle. It could be something else, but let's take a triangle. Okay, it has some vertices here. And then we want to add, say, white dots on this side. So what this means is that there is a dual version with asymptotic branes here, dual to this edge over here. And then if we put a white dot, for instance, here, then it means that those two end on the same 7 brane, while all the other end on different 7 branes. And from the point of view of this stack of branes over here, our basic idea, which is a relatively simple idea to have, actually it's quite natural, is to interpret this as a T-brane. So what is a T-brane? Well, a T-brane is a brane. So you have a stack of brane. Let's say you have n brane. So this is n is the height of this thing here. And you turn on some nilpotent vev for the field, which is valued in the adjoint of these branes. So more concretely, you can write a matrix here with which is valued in the adjoint of un, and a T-brane will be something like you have. I will explain this in more detail later, but you turn on some nilpotent vev here. For instance, you turn on this one, and then this one tells you that you should join these two things. And you see easily how it should be done in general. If the white dots here will specify a partition of n, and to a partition of n you can associate a Jordan form, and so you just add ones like this in the shape of the partition of n. So I will explain exactly what I mean by this, but that's the idea. It's a non-geometric deformation of the brane system. So this is the important thing. It's non-geometric, which means the geometry in the dual version here, in the would-be dual toric variety, the geometry has not changed, but you have just frozen some degrees of freedom. And so, okay, fine, but if you say this, then you've said nothing because, well, as I said, it's non-geometric, so the deformation is invisible. So how do you visualize it? Well, that's the second point. So this is first point. You do the T-brane. And then second point, second step, if you want, you reveal the T-brane. It's a bit like you have a chemical, and then you put some invisible thing in water so you don't see it. But then you can put some chemical which will change the color of the thing, like some chemical reaction which will reveal that actually the thing was not water to begin with. So here, how do we reveal that our geometry was not just plain geometry, but that it was actually a T-brane? Well, to reveal the T-brane, we use more deformation. So we deform using a semisimple vev. So I will again explain and show examples. And this is dual in the brane system to Hanany-Witten moves. So my goal now in the next like 40 minutes is to explain this two-step process in a particular example so that everything is clear. So at this point, it's maybe not very clear, but I will now go through this. Okay, so let me do the example so that we are discussing things, concrete things. So my main example, sorry, I forgot to say one thing. It's very important that in this paper, so while our goal was to understand a generic GTP, so generalized toric polygon, it turns out to be very difficult. And we really rely on a reduction from this brane system, so from the brane web, for instance, to, for instance, a type 2A intermediate frame. And for this, because we rely on this, we can only put white dots on a single edge of the polygon. So here there are no white dots here and here. We don't know at the moment how to put white dots on different edges. We can do on one, because then we put the T-branes, but the problem is we don't know how putting different T-branes at different angles would interact. We are kind of working on this. So I will really not try to address this in this talk. So really white dots on a single edge. This is a very important limit of our work. Okay. So the example I will be looking at is a simple toric diagram, which is this triangle. So I look at the the TN theory. So the TN theory is really one of the most studied and most well-known of the 5D SCFTs. In terms of brane web, it's just what you get when you have an intersection of n d5 branes this way, n ns5 this way, and n 1 minus 1 branes this way. And this is dual to, of course, this is toric, so this is dual to, if I draw the toric diagram, so here I draw for n equal to 4. This is dual to this diagram over here. So this is T4. So this is the brane picture, this is the toric diagram, and now if you want the geometric picture, you just you open the toric geometry book, and then you compute a little bit what this gives, and then this gives an equation, which is W1, W2, W3 equal Z to the N. This is the equation, so that you have this threefold inside C4. So that's a singular threefold. And the claim is that M theory put on this gives the TN theory the same as the world volume of this brane system. Okay, so that's the well-known story. Now, if we look at the singularities here, the thing that makes, I should have mentioned this as well before, the thing that makes this story difficult and interesting is that the singularity is not isolated. As you can see here, the singularity, it's singular along the loci, for instance. Well, it's singular along W1 equal W2 equal Z equal 0, but W3 equal anything. You see, it's singular along a whole line, and you have actually a singularity of type A n minus 1. You see, it's C2 mod Z Zn. And similarly, if you exchange 1, 2, and 3, so you have a non-isolated singularity, and this is what makes the study difficult. In terms of the M theory story here, in the case where the singularities are isolated, then there are many more works, and you can say much more actually.
Is it an orbifold?
Is it? Yes. So this is an orbifold of C3 in this particular case. Yes.
What's the group?
I think it's just Zn times Zn, I guess.
With action
with the standard action 1 minus 1, 1 minus 1.
1 minus 1, 0, and
and 0, 1 minus 1.
Okay.
I guess. Yeah. But okay, we will not use the fact that it's an orbifold here, because the goal is precisely to break this symmetry, because we want to so the goal is, I just repeat here, the goal is to then end this in a non-trivial way on 7 branes and to do the dual in the geometry. Okay, so what we use here is, as I said, a projection to type 2A in a way. So how do we do this in practice? Well, the goal, the way is relatively easy. We want to project it, say, so we pick a direction. So I will pick this direction to project. So we go from M theory to type 2A by reducing on a circle. The circle is one of the S1 inside one of the 3 C-star actions, which are in the toric Calabi-Yau here. And one way of doing it is the following: we introduce a variable. Yeah, we will put it in blue because it's these arrows. So we introduce a new variable y, which is W2, W3. And now we can rewrite this equation as a system of 2 equations. So y is W2, W3. And now I can replace here y by this by y. And then I get W1y equal z to the n. And W1 I will rename by x, just so that it's more standard. So this is actually x. So now what you see is that this is a K3, an an-1 singularity, and then over it you have this this vibration y equals W2, W3. So this is singular, but we can resolve it, and the resolution of this will correspond to the fact that this will correspond to all these intervals here, these n intervals. So let's do this. So this is a cartoon of the resolution of this singularity. We can draw it in this way. So we want to do a toric resolution. So we introduce variables in this way. So we will say that x is, okay, so here I didn't write them down, but yeah, x is, well, z1 to the n, e1 to the n-1, down to en-1. So these e's will give the exceptional divisors. Y is the opposite, so it's e1, e2 squared, en-1 to the n-1 z2, and then z is z1, e1, en-1 z2. So if you do this, then now you have blown up the space, and schematically you can write z1 equal to 0 as a non-compact divisor, and then you have a set of compact divisor, e1 equal to 0, e2 equal to 0, etc. And then you have en-1 equal to 0 here, and then z2 equal to 0. So these are the divisors inside this 2-dimensional space over here.
So y should have z2 to the n then? Is that what you're...
Y should have, oh, sorry. Yes, you're right. Thank you. Yeah. So, and this is important because now if we use this reduction, then we can look at, so branes have appeared. And so we went from pure geometry, M theory with pure geometry on this threefold, and now we have reduced to type 2A with these 6 branes. And the 6 branes are, we can look at where they are. Well, basically where they are is in the original description here, I picked one direction. So I picked this, I guess I picked 2, 3. So I picked that there were branes along the y direction. And so there are the 6 branes. They are described by some ideal. So I can describe it as the ideal of the D6 branes. And this is the ideal here generated by y and z to the n. But now if we expand this in terms of these variables here, you see that y actually divides z to the n. So it's just the ideal generated by e1, e2 squared, etc. So then and z2 to the n. And so what this means is that there is actually, let's put them in yellow, there is one brane kind of wrapping this one, and then there are two wrapping this one, and then three here, up to n wrapping this. And so you actually do see a quiver here. There is and this is the quiver you get by the reduction of this toric diagram over here. And the quiver would be, there is one brane, two branes, etc., n-1 branes, and n flavor branes over here. So that would be the effective quiver for the theory.
You are now in type 2A. What did we do?
Sorry, yes, it's in type 2. So yes, this was M theory here. And then I did a circle reduction here. So now I'm in type 2A. And these are the 6 branes.
You're on one, which direction do you choose for reducing? This one? How do you say this one?
Which direction? I choose, so yeah, so there are 5 transverse directions to the threefold here. And then when I reduce, I have picked one direction. So it's wrapping these 2 additional directions. So I've reduced on one circle. So in the dual direction, you have, this is one, and then the, so this S1 here is what this one here is inside a C star, one of the 3 C star actions. So it's wrapping these 2. So these are the 5 original directions plus the 2 directions in this C star. I don't know if this is
What becomes of each object? So all of them become geometry?
Well, here we go from pure geometry to this. If you want, okay, maybe it's easier to see it from the other way. If we start from the, sorry, again, yeah, the other way is to go from 2B. It's kind of intermediate between 2B and M theory. So if you go from the brane web, which actually I drew here, then you have this picture, right? You have this, and then you have 2, etc., 3. And then here n. So that's now the 2B picture. This is the brane web. And these are D5. And so you just T-dualize the D5 to make them D6s. And then you end up with this geometry here. And that's another way. So this is kind of the intermediate setup. But this setup is useful because this is where the T-brane formalism can be implemented. So let me tell you one thing about the T-branes. So how do we do the T-branes? So the idea of the T-brane is that this is a tachyon condensation between branes of 2 dimensions higher, which give rise to these D6 branes. So we want to realize these D6 branes as tachyon condensation between D8 and anti-D8. So first, to illustrate this, for those not too familiar with T-branes, so I'm also not an expert in T-branes. I saw Raffaele was in the audience, and I don't know if so they are experts, so you can correct me. But my simple vision of the T-branes and the tachyon condensation, well, I will start with the tachyon condensation, is as follows. The simplest example would be to look at D7 branes. Let's take n D7 branes. Like this. These are n D7 branes. There are 2 transverse directions. So the transverse directions I call Z. So this would be at Z equals Z1, Z equals Z2, up to Z equals Zn. I take n, this 7 brane, parallel D7 brane, so very easy. And the idea is to see this as, to define this as the co-kernel of a certain map. A map which goes from what to what. So let me define. So let's say that R, by R, I will mean the polynomial ring in Z, in a variable Z. And so I take R copies of, sorry, I take n copies of R, and I take R copies of, sorry, n copies of R, I have a certain matrix. Which matrix do I put here? I put Z minus Z1 up to Z minus Zn. So these are just the equations of where the branes are. And the idea is that if you look at the co-kernel, so if I use the fancy math, I take a sequence like this. This sheaf here tells me where this matrix is non-invertible. In other words, it tells me, when Z is equal to one of the Zi, then I have something. If Z is not one of the Zi, then I have nothing. So this defines a sheaf, and this sheaf characterizes where there is some D7 brane in the space. So yeah, so that's the idea. And so you see that the equation of where these several branes are, these are given. So this matrix I call T. And if I look at the equation determinant of T, well, this is just Z minus Z1 up to Z minus Zn. And if I solve this equation, I get that either Z1 or the Z2, etc. And it gives me where the D7 branes are. So that's the whole idea. That's the only thing I will use from here. The fact that we can realize a certain brane configuration as just the locus where a certain matrix is non-invertible. And I want to do, so this was like the simple setup. I want to do the same thing with this configuration over here. So okay, in view of time, I will do a slightly simpler example rather than carrying on with n everywhere. Let me just show you the example with n equal to 2. So let me do the T2 example. For the T2 example, we have, so let's write again the three toric coordinates. So Z1 squared E1, Y is E1 Z2 squared, and Z is Z1 E1 Z2. And now, if I redraw the same picture as before, now I have only one compact divisor. This is the A1 singularity. There is one P1, and this is covered by one brane. So there is one here, and there are two over here, and 0 here. And this is easily written as follows. You write the tachyon matrix. When you want to account for this brane here, which is E1 equal to 0. So you put E1 here in the matrix, and then you have 2 at Z2 equal to 0. So then you have a 2 by 2 matrix at Z2 and Z2, and zeros everywhere else. So the one complication that we get here is that now we are not on an affine space, we are on this resolved space. So you need to keep track that everything makes sense, so you should have the right degrees, and there are a whole lot of complications because of this. But okay, here things will be, here the things should be easy to follow. Now the matter content, the matter on this brane system is given by the possible deformations of this, the fluctuations of this T-brane background. So I should ask, what are the possible fluctuations? If we just have a stack of D-branes, the fluctuations are given by, well, a matrix, an adjoint matrix, adjoint of UN. So we should ask the same thing here. And well, in order to know what is possible, there is kind of a recipe which tells you the following. So how to phrase it? Yeah. So if you have any, okay, let's say it in this example here. If the T matrix is this, then the fluctuations are all the matrices that you can write, but you can always cancel by multiplication on the left or on the right by this matrix T. The reason for this is easy to understand. I should have left space. Yeah, let me erase here, and I write over here the explanation. So you see the matrix T goes from this R to R. And now we want to have a fluctuation of T. So let's write 2 copies of this. 2 copies. And now a fluctuation is another matrix that goes this way. And we want to be able to not count everything which is just a change of basis on either the D9 or the anti-D9. So this would be the D9 bar, for instance, and this would be the D9. So we want to not count anything which is just a change of basis on each side, which means that this delta T belongs to, it will be any matrix, but quotiented by the ideal generated by T multiplying on the left and by T multiplying on the right. This is to account for the fact that I can define independently a change of basis on the D9 or the anti-D9. So here I can just apply this recipe, and being careful about the weights and everything, I end up with a form of the fluctuation, which is, so let me write this most simply as Z2 times the identity matrix. So this is 1 by 1, this is 2 by 2, and now you have possible fluctuations here. And what you find is that the fluctuations take this form. So let me write T plus delta T. So here I still have E1, I cannot deform this. And here I find I can put some matrix that I call Q1 tilde, which is a 1 by 2 matrix times Z1. This is because of the weight conservation. And here I find Q1 over Z1 squared. And here I find that I can add some matrix Z1 times some matrix, 2 by 2 matrix. So the interpretation of this is, as you can guess, if I write the quiver that corresponds to this is the quiver, and then I have maps which are the Q1 tilde and the Q1, and those things are located, they are kind of localized at the intersection here between the two loci E1 equals 0 and Z2 equals 0. And in particular, it's very important that this term here is well defined, because you see it's in 1 over Z1 squared, but Z1 equal to 0 is here. And in particular, it does not intersect with the locus, the blue locus here. So you can have this thing turned on. And if you work out exactly in all the tachyon formalism, which I don't detail here, you can look in the paper, then you see that indeed, this is the correct normalization of terms that you should input. This is completely dictated by the various conditions. So by this condition here, and the choice of toric variables that we made here. Okay. But now what it appears is that here you can make a change of basis, as I said, on the left and on the right. So you can multiply on the left and on the right by certain matrices here. And you can put this matrix in the form E1 over here, and then you can set this to 0. So you see the value that you have in the bifundamentals here can be absorbed in a pole here, and that's the whole thing. Sorry, so you have the same thing here, Z2 times the identity plus Z1 times some field phi. And this field phi, this is just a computation, it's just a change of basis computation, diagonalization, is minus m over x, where m is the meson matrix, so it's a 2 by 2 matrix, it's Q1 tilde, it's a 2 by 2 matrix, and x is this coordinate here. And now you see that it is a pole, so that really it's really important to see that if you look from the point of view of this brane over here, you see that x equal to 0, x is Z1 square E1, so x equal to 0 on all this, let's put it in purple, on all of this, you have x equal to 0. And so you see that from the point of view of the yellow branes here, there is a pole, it's a Hitchin pole in terms of x. And this pole is given by this matrix here, this meson matrix, which should be a nilpotent matrix. This is a nilpotent matrix. And so it means that up to conjugation, you have two choices for this matrix. Either you set 0 and then you don't have a pole, so then you have nothing. I mean, you don't have any constraint, or you do have a pole. And then if you have a pole, then it imposes some condition. And that's the whole claim here, is that this pole is precisely implementing the white dot. So if M is nilpotent, sorry, if M is different from 0, but is nilpotent, so that means that M is up to conjugation this matrix here, then we actually have the geometry. So remind you that we are looking at the geometry of Tn with n equal to 2 here. So we actually have this geometry here with a white dot. And we have imposed this condition. Now, as I said before, this doesn't show up on the equation because I remind you that the equation is given by xy, sorry, it's given by so we had the K3, so the K3 was xy equal to z to the n, so here it's z squared, and W2, W3, so this was W1.
Why do you call it K3?
It's local, it's this singularity here.
But it's K3 is compact smooth.
Yeah, okay, it's a local K3, sorry. Let's say AN singularity, maybe it's
Why do you like it? It's bad. You don't like it?
No, yeah, okay, I also don't like it, but it seems to be I've heard people call this a K3, but okay, let's say an AN minus 1 singularity. It's better. You like A minus 1?
No, I mean, you know, it's okay. You could call it Duval.
Oh, Duval, okay, very good. Let's call it the Duval singularity. So
Antoine, sorry.
Yes.
Can I ask one thing?
Yes.
Maybe you said, but I got confused. So the pole that you see there on the location of Z2 equal to 0, is it due to the E1 equal to 0 brane, no? Not on the to the Z1 equal to 0, because X also vanishes when E1 equal to 0.
Sure, yes. So
Okay,
yes, so X.
Okay, sorry. I thought that you meant Z1 equal to 0, but it's rather E1 equal to 0 that creates the pole on the stack.
Right, it's X equal to 0. X is Z1 squared E1, so it vanishes at order 1 in E1, so it creates a pole of order 1 in E1. Yeah, that's right. That's why I colored it in purple, to say it's really on all these locus that you have this, and in particular, it does intersect with the Z2 equals 0. So yes, there is really a pole.
I think that the brane in Z1 equal to 0 plays really no role here now, no?
Sure, yeah, there is actually no brane. That's why I didn't put any yellow thing.
Okay.
It's empty. I could have,
yeah,
I can remove it. I can do this maybe.
Thanks.
Yeah, thank you. Yeah, so let me just arrive at the equation here. So so before we had y, right? Y, but this is really the determinant of T, and the determinant of this matrix. So let's write T explicitly. T after the transformation, so T, which is here on the right. If I write explicitly, it's like E1, Z2, Z2, and minus 1 over Z1, E1, and 0. So that's T. And as you see, the determinant doesn't see this thing here. So it is still E1 Z2 squared, which is Y. So if I then solve for this, then I recover the initial thing. So it doesn't see the difference. But as I said, this is because now the geometry is partly frozen. And one way to see it is to turn on another fluctuation here, which will be semi-simple, so it will really change the eigenvalues here. And so I will put it in red. Let's say we turn on some other value here, say alpha Z1. It has to be alpha Z1 because of what I wrote. No, sorry, I didn't write it, but I see. Yes, I wrote it here. The fluctuations of the 2 by 2 matrix have to be proportional to Z1. So you can turn on an alpha Z1 here. And then if you replace by this, then the determinant, as you see, changes, and there is an additional factor of plus you see there is E1 from here, and then alpha Z1 and 1 over Z1 E1 that arrive in the determinant, and it all simplifies, giving just plus alpha. So, and then if you solve, then you can solve for y here. You can say that y is W2, W3 minus alpha, and then put it back in here, and then you get that W1, W2, W3 equals to Z2 plus alpha. So that is the equation after having turned on the T-brane and doing a Hanany-Witten deformation. And in the brane web, what we have done is very, very simple here. We started from here. So initially this was the brane web. Then we have turned on the white dot. So this element here is like moving this segment out. And now that this is done, there is a possibility for doing a Hanany-Witten move, which takes this 7 brane here and move it across, and then it detaches completely, which means that there is no singularity left, and this indeed is completely smooth. So yeah, so sorry, I think I went a bit quick on the, well, I don't want also to spend too much time on the technical details. I just wanted to give a flavor of what this is. And so let me now show some applications and checks in the next 10 minutes. And
so, sorry, Antoine, can I ask just one curiosity?
Sure.
So, I mean, in principle, you could also turn on some nilpotent deformation that is not singular, there's no pole. No, you just bind the two guys of the stack in Z2 equal to 0. Because you had 2 branes at Z2 equal to 0, right?
yes.
So I was curious of what happens to your toric diagram if you do that.
So you want to turn on a nilpotent
the phi
proportional to Z1 here.
Yeah, I mean, there is an extension. There is part of the extension group that also has a nilpotent phi matrix, right?
Yes. Yes, if you do this, I think nothing should change.
The geometry doesn't change for sure, because it's still nilpotent.
Yeah.
But I was curious to understand.
But I think you can really not, and you will not be able to do even like a thing like this to reveal anything that has changed. Because in a way, if you deform by Z1 here, you deform by Z1 on the Z2 equals 0 thing. Z1 equals 0 is over here, doesn't talk to it. So I think it won't change anything, but we could do the computation.
Okay.
Yeah, I think it doesn't change. It's really crucial that it appears as a pole, and that's how it can talk to the rest.
Can
you hear me?
Yes.
Hi. I think that what Raffaele proposes is something related to non-compact branes, and it's not a verb for the B fundamental in some sense. So that's why it doesn't appear as a pole.
So it's
so it doesn't. It's not something along the Higgs branch of the 5D.
I understand. So it's something that is in the flavor sector, say.
Right.
Okay, I see. Okay, thanks.
Yeah. Okay. Thanks, Roberto. Okay. So now let me say. Well, okay. First, how does this generalize? I've done T2 in detail. Well, the general story for Tn is very similar. I will just write one formula and then show some applications and checks. So for Tn, in general, a very similar argument to this will give us a formula of this type, W1, W2, W3 equal. So now the white dots are given by a partition lambda, which you can write as lambda 1, lambda r of n. And then this is just the product of the z to the lambda I plus some constant alpha I W1. Okay, so that would be the deformation for Tn. So this is Tn with white dots given by segments of length lambda 1, lambda 2, etc. Okay, so now can we make some checks and interpretations of this? So I don't have too much time, but I will. I think in the Quiver meeting time is relatively flexible, is it?
Sure.
Sure. Okay. Very good. So I will try not to take too much time, but I want to show these few checks. So yeah, check number one I would like to make. Well, no, first I would like to just say one more thing with this. The brane interpretation of this is a recombination of this whole, because of the pole here, all the, the two yellow brane here plus this yellow one here, all recombine, and that's why it smoothes completely. But then if you do the same thing with a bigger example, let's say T3, T4, T5, then you find that this the wave that you can give will realize the various quivers for the various Slotowitz slices of the an-1 algebra. And so in a way, this is just the geometric way to implement these transitions. And actually, we show in the paper that using these fluctuations here, we can really reproduce all the Kraft-Procesi transition in type A. So that's one thing, but it's a bit technical because it uses all these matrices, so I won't show it here. So this was, let's say, check number 0. But now let me show check number 1. I will take, check number 1 should be that if you, sorry, actually, I forgot to say one thing. This is Tn, but now the claim is that this works for any GTP. So if you have any GTP of any shape, you can always take the side that you want, the edge that you want, say this one. You can always put it vertically this way, and then do the same kind of things as before. Here you will have, in the reduction, you will have an A, let's say this is length n, you will have an A n-1 Duval singularity, and then you can play the same game. And basically what it tells you to do is to replace in the defining equation here of the Duval, you see the Duval singularity is defined here, you just deform it by terms of this shape here. So we can actually do it for anything, and I want to show an example where it is slightly different than the triangle because we are bored of the triangle. So let's take a box. So this will be our toric diagram. I'll take off size, and well, let's put numbers 2 and 3. So in the dual brane system, it's just 2 branes over here and 3 over here. So very simple theory. We know everything about it. But the point is that we want to put a white dot here and use the geometry argument and to see what it gives. And we know what we expect is that if we do this, then we know that we can put boundary conditions like this. And then if we try to move this brane all the way across here, then if you work out the whole thing, you get this. Okay, let me not try to draw the. So this is just a little brane web exercise. And in other words, this should be the T3 polygon with no white dot. This is T3. So this is T3. So in other words, the 2x3 box with one white dot should be equivalent up to a Hanany-Witten move where you take one brane from the far right to the far left. It should be equivalent to T3 without white dots. So let's check this. So again, first we need to find the equations for this. So you open the toric geometry book and you find that, okay, the equations, it's actually a complete intersection between two Duval singularities. Okay, so that's what it is. And then we use the trick.
Probably not a complete intersection.
Sorry?
Probably not a complete intersection. I think it's much more complicated.
I think this one, the toric space associated to this should really be just this. It's should be a complete intersection in C5. So I agree that sometimes you get much more, but in this particular case, I think it's really just this.
But already for the case 2x2, it's not. Why is 2x2 is not and 2x3 is?
Oh, but 2x2 should be as well. So you say, let me try to understand. What do you say is not a complete?
2 by 2. So that's Z2 cos Z2 oblifold of the conifold with the action 1 Z2 on one, one and 1 Z2 on the other. Well, I can, okay, maybe
it should be just same as this with the 2 here.
I'll check. Okay.
No, it's not if you compute the Hilbert series. It's not a complete intersection.
I see.
No, but
Even for the Z2 orbifold of the conifold, you have 9 generators. 9
Yeah, but
variables.
he's taking Z2 cross Z2 or Z2 cross Z3.
Yeah, it's even more. It's even worse.
Okay, we'll have
okay. We can maybe check it after.
Okay. Yeah.
I think it should be this. I'm just talking about the toric. Read just the you define this toric diagram. You compute the toric variety and find this.
I think we are talking about the same, but it's a question of computation. Okay.
Yeah.
Right.
Okay. Okay, and so now if we want to add this dot over here, then it amounts, as we said, just by a generalization of what I said before, to adding just some constant over here. Say alpha W2. If we put it on, we have to label the edges, and then you get this. And now that you have this deformation, you can try to solve, and you see that you can solve for W2 by putting it back in here. So if you multiply by alpha, then you get that alpha Z cube from here is alpha W2, W4, and then alpha W2 is W1, W3 minus Z squared times W4. And then if you solve it, you then get that W1, W3, W4 is equal to alpha Z cube plus Z squared W4. So you find this one equation. And alpha, it's the thing that labels, so it's alpha equals 0 over here. And then when you turn on alpha, you start moving the brane. So here it should be alpha goes to infinity. You can also see alpha as valued in a P1. And so in the limit alpha goes to infinity, you basically this term dominates, and then you can drop this one here, and you recover W1, W3, W4 equals alpha Z cube. And this is indeed the equation for T3 that we saw at the beginning. So this is the kind of checks you can do, and you can do it on other examples. And it gives the various consistency checks. Then let me give a check number 2. Again, I won't elaborate too much, but another way is to check that the matter is the expected one. So what do I mean by this? Let's take as an example. So I will go back to the let's say T4 example. So in the T4 example, I will make a table, maybe on the next page. There are 3 interesting cases. One is the T4 without any white dot. One is the T4 with 1 white dot, and one is the T4 with 2 white dots. So this would be partition 1 to the 4. This would be partition 2, 1 squared, and this will be partition 2 squared. We don't do more because then the rank of the theory would be 0 or negative. So okay, so the rank of the theory here is 6 because there are 6 internal dots, and well, here it will be less, etc. Now we can try to see what are what properties of these theories can we extract from here. Well, the one thing we can try to do is to compute the global symmetry. And okay, there are various ways of doing it, but since this is the Quiver meeting and I haven't mentioned magnetic quivers yet, it's time to do it. So we can compute the magnetic quiver. So we take the brane web and compute the magnetic quiver using the well-known algorithm. And we get this quiver over here. And then the balanced nodes are all of those. So we read from this that there is a symmetry which is SU4 cube. Now, if we go to this case here, then the quiver changes slightly. 1, 2, 3, 4, 3, 2, 1. But now this partition tells us to put here 2 and 1. And now if we look at the balanced node, which tells us about the global symmetry, we find all of this. And so we see an SU8 times SU2. And now if we do it in the last case over here, 1, 2, 3, 4, 3, 2, 1. And now everything is balanced. And this is because this is, of course, the E7 diagram. So we expect those symmetries. And this should be visible from the geometry. So, okay, now we have a way to write down explicit equation for these geometries. So here it was W1, W2, W3 equal Z4. Now here, instead of Z4, we put Z squared times Z squared plus alpha W1. And here, instead of Z4, we put Z squared plus alpha W1, Z squared plus beta W1. Okay. And okay, so then we can take those equations and resolve until the space is completely smooth. So we have to do a certain number of large resolutions and then a certain number of small resolutions. And then we have a certain number of curves that appear. And the procedure, which has been explained in the CFD papers, and there's a whole literature by Fabio and Craig Lowry, Lin, Sakura, Inan, Laksha, Cyril, Simone, and I probably forget other people, but there is this CFD approach. You can write a graph where you have curves. So let's do it for this case here. So you have curves.
Antoine,
Yes.
This middle one is not equivalent for SU3 with the 7 flavors.
This one here is SU3 with 7 flavors.
The middle, yeah.
Yes. It's possible. Yes, right. Well, SU3 with 7 flavors would be, yeah. So you have SU3, and then you add a flavor here, and then you have to resolve the thing. So then you have this like this. So that's the no. So SU3 with 7 flavors. If I made this correctly, should be the E7. Ah, no, sorry, no, yes, no, you're right. And here you have 2, 1. Yes, that's right. That's this one, yeah. So it's SU3 with 7 flavors at the appropriate level, but at infinite coupling, of course.
Yeah. Mm-hmm. So
yeah.
But is this something which can be read from the equations, or it requires more work?
Ah, yeah, no, I don't know how to read it from the equation.
Mm-hmm. Okay.
What do you mean? What you don't know how to read from the equation? The flavor.
What?
I think he can you read that it is SU3 with 7 flavors from this equation? I think that's the question.
Yeah. Sure. When you do the resolution, you see that there are now that many compact devices as the rank, and they have some certain ruling. Right? That's the standard geometric engineering and M-theory picture. So I think here it was just to check also that you see the flavor from these equations, but these will have compact divisors, and if they have a ruling, so you can collapse them to an A2 singularity, then you know that it's an SU3 gauge theory. And then a number of flavors is basically in that partially resolved phase, how many, curves there are that are also sort of mass or have a certain mass that are charged under these. So that we can, of course, read off.
Yeah. Okay, that's some work, but yeah.
But you can't read it off from the equation.
Yeah, okay.
Resolve it, right? So there are loads of blow-ups that we have to do.
Yes. Indeed. So actually, so I was about to draw these diagrams. So after doing all the blow-ups, we have here a collection of curves. Actually, let's draw all the curves. But then some of them have self-intersection -2, which are those one here. So okay, to be more precise, here we are. I'm drawing the graph where the dots are curves, and the intersections are given by the intersections of these divisors. So these are the non-compact divisors, which are called D. So DA, DB. These are non-compact divisors, and then you intersect with the unions of all the compact ones. And so this matrix here, let's call it GAB. So this is the matrix of intersection. This is what I'm drawing here. So the self-intersection I paint in purple. I guess I should do it in green to be consistent with the literature. Okay, let's use this green. And then the other that I've not painted are -1 curves. And okay, it gives some graph like this. So this you obtain doing this repeatedly, a lot of resolutions. And what you read from here is that indeed the global symmetry should at least contain these 3 factors of SU4, which are these 3 Dynkin diagrams. And then there is a certain matter content which belong to the representations. So this one would be in the 4 bar of a given of this pair, and then trivial under the next one, etc. Permutations of this. And okay, we don't learn much more here because the symmetry is SU4 cube, so that's already apparent here. So now we want to do the same on this deformed equations and see if at least the intersections are compatible with the symmetry enhancement that we read from here, so the E7 and the SU8. So if we do the same thing here, we'll get this curve here. Here. Okay. And the intersections. Okay, does something like this. So here what we see is that there are 2 SU4s and 1 SU2. So the SU2 is this one, and the 2 SU4, actually they should enhance to an SU8. And okay, we don't see it here, but at least the matter content that we see should be compatible. And well, it is. If you look at, so I should have written it. But so if you look at all these -1 curves over here, all of those, then it gives you a matter content, which is, so this is for instance the 4 bar again, and 1 of SU2. Then this one is in the it's in the antisymmetry here, so it's in the 6, and then 1, 1, etc. You do it for all of them, and then you find that all of this can be arranged into representations of SU8, SU2, which are the 28, 1 plus 8, 2. So these are representations of SU8, SU2. So at least the resolution shows that the geometry is compatible with this enhancement. And if you do the same thing here, you find also something. You can just draw it like this. And then yeah, find something like this. And again, you can count. Here, here, here. And again, you find representation content that's compatible with an E7 enhancement. You get this gather into the 56 representation of E7. Okay, so that's another check of the proposal. And now I will conclude with one last image.
Are you saying that these are the generators of the chiral ring?
No, so yeah, these are, yeah, so that's a good question. Actually, this is so these are not the generators of the Higgs branch chiral ring. So these are operators which are in some other sector, and I don't know exactly which operators these are.
I see. Yeah, I think in the chiral ring you'll have the 28. There is 3. So do you see the 3? The adjoint of SU2?
You mean in this case here? No, so there's no adjoint. But even here, actually, sorry. Yeah, well, yeah. So there is no adjoint. So this is really, we are not counting here the Higgs branch operators. So it's a relatively weak check if you want, because we don't exactly know which operators they are. So maybe there is a way to look at some index computation and find which they are. But we haven't done this yet.
I see.
So let me now give a last, to conclude.
You won't see the you won't see the fourth rank and symmetric, the middle dimensional of SU8.
You say you won't see it?
I'm asking. Will you?
I don't know. You mean in the
in this type of diagrammatic?
Yeah, no. You just see some low level.
I see.
Maybe there is a way to extract more, but
yes, okay. You would have to. So these are just Kuma-Rafa variants for like genus 0 curves, but of course you could also look at other curves and higher degree curves. So this is just basically, the simplest data you can extract that then also contains the information about the enhanced flavor symmetry. But there's more. There's like a whole sequence, right? You can sort of compute all these invariants in principle.
The main problem with these invariants is that it's very hard to understand the gauge theory interpretation. There's plenty of invariants, and most of them, there's no good intuition.
I guess on the Coulomb branch, it's clear, right? It's just some matter, some hypers. But you're asking on the CFT side.
On the Coulomb branch, they cannot transform under this symmetry because this symmetry acts on the Higgs branch. And so there could be some.
But these flavor symmetries, they're basically broken on the Coulomb branch, but you can still infer what the UV flavor symmetry is from the all these charges that Antoine wrote down there.
Yeah. I mean, even for simple cases, it will be good to demonstrate what is going on, because the connection to the gauge theory gets lost very quickly. Even on Coulomb branch. I mean, let's say you do Coulomb branch operators, then we want to understand what they are.
Maybe this is a discussion for afterwards, because
we can keep discussing. I will just draw.
Discuss this, but,
I will just draw one picture, and then we can go to the discussion. Just Hasse diagrams haven't appeared yet in this talk, so I couldn't tolerate this. So let's draw the Hasse diagram for this theory over here. So it is, for instance, it is obtained via the Quiver subtraction. So the Hasse diagram for the Higgs branch now. So if you do it, you obtain this diagram here. So you have 3 E7 transitions and 1 E6, and then here you have 3 A1 transitions, and from here you have 3 A7 transitions, and now A3, A3, A3.
Which quiver you're doing? The
so it's the top one. Sorry, this is the top one. The left one. So this is T4.
The left, I see.
The left one, yeah. But now I'm going to do all of them on the same diagram. That's why I was a bit. And now, what is the interpretation of the white dot? As we say, this is really the Higgs branch interpretation of the T-brane picture. The T-brane tells you that you turn on some nilpotent VEV, which freezes part of the degrees of freedom, part of the freedom you have to move on the Higgs branch. And as I said, I don't remember where I said it, but the concept of Slodový slice appears if you do it on the TN, the resolved diagrams. And the analog here will be some kind of like Slodovy slices, but not for nilpotent orbits, so they are not called Slodovy slices, they are just called transverse slices. And so the effect of turning on, for instance, this alpha here amounts to picking, and you see we not only had to turn on alpha, but we had to pick one direction out of 3. So this means that actually we had to pick one of the 3 A3s and break it in some way. So for instance, I will pick this one. So this is the effect of setting alpha non-zero. If you have alpha equal to 0, you sit at the bottom, and then when you turn on this alpha in this equation, then you get here. And so that should be the resulting diagram, which is now I don't know how to draw it. Let's put it in green. So this part here should be the diagram for the Higgs branch of the deformed space here. And indeed, if you do quiver subtraction on this quiver here, well, you do find this reduced diagram. And then if you turn on beta, then again, you have to choose which way to go. But here we are breaking the SU2. So turning on beta, you can draw it in another color, red. So this thing is beta different from 0. This is this beta over here. And alpha, of course, is still here. So by adding these white dots in terms of the Higgs branch geometry, it means that we are reducing the Higgs branch, reducing it to a transverse slice from the top. And indeed, well, here you see the E7 singularity. This is indeed this E7 symmetry. Here we have SU8, SU2. We can read it as SU8, SU2 here, and the 3 SU4s over here. So there are really multiple ways of interpreting these white dots in terms of the Hasse diagram. It's like changing where you set the root. So it's taking a transverse slice from a higher leaf rather than the origin. And here we have given this interpretation in terms of equations. So if you have any toric diagram and you put white dots on one edge, then we can give you a set of equations. I've shown almost only complete intersections here. I mean, almost only hypersurfaces actually, but we can do it more generally. So now there are plenty of other questions. Sorry.
If you'd like to turn on a white dot on another edge, this would be the other choice that we have in your Hasse diagram, right?
Right, yeah.
Which was better if we go to the left, then
yeah, here.
a different edge. Okay.
Yeah, if we want to go here, yeah, exactly. This would be putting on another edge.
And if we go to 3, 1, it's smooth, I guess. Yeah.
Yeah. But the problem is we don't also, okay, there is a natural guess. The natural guess would be, okay, then you just deform this guy with not W1, but W2, for instance. This is the obvious guess. But we haven't been able to motivate it. We cannot. So I haven't emphasized too much, but the whole T-brane development is very precise, and you just compute and you get this answer. So that's why we are confident in this. We don't know how to make this work for dots on different edges. So, but that's actually my conclusion. Probably the language will need to be changed. And we know that it's a bit awkward to work with equations when you have toric geometry. Toric geometry works well in terms of these combinatorial objects, the diagrams, and you should think of various elements of the toric diagrams as the divisors, these are the dots, and then resolutions are triangulations, etc. So it is probably a bit inextricable to try to work out with explicit equations all along. And now the future thing is to try to have a more global point of view and to try to find the combinatorics of these diagrams using more like toric geometry and deforming toric, but not writing everything down in equations. And another point would be to connect better to the works done in particular in this paper that I mentioned at the very beginning, where we do have explicit geometries, even non-isolated explicit geometries for these various theories. So for instance, the one I've shown here, well, at least at rank 2 and maybe a bit more. And they also have the interpretation of certain moves, like these Hanany-Witten moves, where you move one brane from one side to the other. So I think it would be nice now to connect with this. Okay, but this is a first step, and I will stop here. And if you have any question, I'm happy to discuss. So, thank you.
All right, let's thank Antoine. Questions?
Can I ask one?
Sure.
So thanks a lot for the talk. It was very nice. So you described how to compute these fluctuations for the tachyon by using this the homotopy category essentially. No?
Yes.
Diagonal. But this we know that it works very well in the affine case, no? Whereas you were not in the affine, you were always projective, I guess, no? Because you had the resolution.
Yes.
So I was wondering whether, because we did a lot of these things, and we always, so we know that theorems are there for the affine case, whereas for the projective, you have to be a little bit more careful. And I was guessing, I was asking myself if you had encountered some problem, because there are no theorems available as far as I know.
Yes, so yeah, that's a very good question, and this is indeed a point that confused us for a long time. So there are two points to answer this. So so one point is that we in order to, so I didn't show the general case, but in order to get to this equation here, we basically do it patch by patch. So we don't write a matrix the full matrix at the beginning. We write it patch by patch, and then the diagonalization, so the analog of this step here, is done patch by patch. So you start from the left and then you move it.
So in that case, you could have set to 1 all the things that you have in the denominator, because they cannot vanish there, I guess, no? So if you're in a patch in which Z1 cannot be 0, so then you set it to 1. So just dividing by it is irrelevant, because it's
well, but you're doing it for each, so you're still carrying out the pole, because at the end you still
the pole for E1, yes, I mean in your example, but Z1 for instance is totally irrelevant.
Yes, it is irrelevant, but then there is a second condition, so you have to do it patch by patch, but you also have to at all times be like covariant with respect to all the C-star actions, and then you cannot have an E1 alone, for instance. So whenever you have one variable, you have to carry all the others. So we kind of imposed by hand that you're doing it patch by patch, but you always
keep track of the C-star,
all the C-star actions,
all of them,
at all times.
Okay.
And if you do this, so this is this is kind of technically what's a bit complicated, but then if you do this all the way, then it really comes out with this beautiful form with all the factors and everything.
So basically you have the form of the tachyon for each patch.
Yes, there is that's right. So in principle, indeed, you should do it in a more, so I know Andres was always talking about another approach using this, the orbifold approach, where you don't have to do it patch by patch, but then
because
as you know, then the sequences are longer, the complexes are longer. So we tried to play with this a bit, but this is just more complicated, and in the end this one was enough to give the answer. But that's of course a very central technical question. So thank you for asking.
Thanks.
Antoine?
Yes.
Thank you for the interesting talk. Actually, so let me retract. The 2x(n) boxes are all complete intersections. So sorry about interrupting. What happens for the non-complete intersections? So there, do you try to find out of the relations the AN singularity that corresponds to the edge on which you are adding the right nodes to, or how do you identify for a non-complete intersection the correct relation that has to be deformed?
That's a good question. We haven't really done examples where this is you have a non-complete intersections, but I believe so. There is, I think you know the work of Altman, and he gives the deformations for any situation, including if it's non-complete intersection, in terms of a local, like he gives a basis of the tangent space in terms of the deformations. And so there is always a possibility to extract one edge equation, which will be of the form of this Duval singularity, and many others which do not involve that particular equation. And the claim is that you should modify only that one, This is at least my understanding. But we are actually working on this and trying to check if it makes sense, if it agrees with what we expect physically. But I believe the answer should be in this Altman.
Modify which one?
So there is always, let's do it here. When you have a polygon like this, then you will have many equations, but there is always one which will be of the form x, y equals z to the n. And where x, y, and z are kind of the variables associated to this edge, and this edge. And there is no other, and you can choose a form of the equations so that no other equation has exactly these three variables. And then it tells you that this equation here you have to modify according to our prescription, and the others you don't touch.
Okay.
But again, we haven't, I didn't mention this because we don't have too many checks of this. And so we have checks where it's non-hypersurface like this, so it is complete intersection, but not hypersurface. But non-complete intersection, we haven't checked. Also, probably, as I said in the conclusion, probably it's just not the right language to try to use these equations. I mean, this will become very, very messy, and there is probably a more elegant way to do it in another way. So,
Okay,
but yeah, thank you for the question. That's, of course, a relevant point as well.
So what will those deformations look for grain tilings?
Okay, that's another good question. Actually, we wanted to have a look at this. So the answer is I don't know. We believe that somehow it changes the tiling in a way that we can discuss, but doesn't seem to really. I mean, okay, I won't say much more here, but we have some conjectures, but they are not very conclusive for now. It's also hard to know. So this is in, maybe I don't know if the others want to comment on this, but we try to work this out with, I think Diego was here in the audience, and Guillermo, and Sergio, and Julius. Yeah, that's so we try to look at this, and the answer is we don't know.
There is no answer. Yeah.
There is no answer, exactly. But we did consider the question. It is an interesting one, but yeah, no answer at the moment.
Not yet.
Not yet.
Are there more questions? Well, I would say let's thank Antoine again.
Thank you.
Let's move to the unofficial part.